Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 25th, 2026, just 2 days ago. It proves that aggregating answers from multiple copies of the same model isn't just redundant, but actually allows designers to reach solutions that are mathematically impossible to elicit from a single model. The paper is titled Power and Limitations of Aggregation in Compound AI Systems, and as we'll see later, the mechanisms driving this performance boost are quite fascinating. To understand how this works, Figure 1 illustrates the 3 key mechanisms the authors identify. In the first panel on the left, we see feasibility expansion, where the aggregated red point actually lands outside the shaded feasible region of a single model, unlocking new possibilities. Then in the middle, support expansion shows how combining 2 limited outputs creates a result with richer features that neither had alone. Finally, the right panel depicts binding set contraction, where the aggregation pulls the result away from the restrictive boundaries and into the safe interior of the solution space. Moving to the experiment, Figure 2 visualizes output vectors for a reference generation task using GPT-4o Mini. On the left, the heat map of L2 distances shows that aggregated outputs, the bottom rows, are distinct from any single prompt. The middle and right panels confirm this separation in 3D and 2D projections. Specifically, the aggregated results, marked by the yellow diamond and purple square, land in a unique semantic region far from the individual prompt output shown as stars. Okay, Table 1 connects those mechanisms to specific aggregation rules. The first row indicates that intersection aggregation enables feasibility expansion and binding set contraction, but it cannot achieve support expansion. Conversely, the second row shows that addition aggregation succeeds at support expansion and binding set contraction, yet it fails to implement feasibility expansion. This distinction highlights that different aggregation methods are complementary tools for overcoming specific model limitations. Alright, following the theory in Table 1, Figure 3 presents the empirical validation using GPT-4o Mini. It visualizes the 3 mechanisms: support expansion on the left, binding set contraction in the middle, and feasibility expansion on the right. Here, the blue and green dots are individual prompt outputs, while the red dot is the aggregated result. The key detail is the gap between the red dot and the purple dot, which represents the single model's best attempt to match the aggregation. Because these points clearly do not overlap, the data confirms that aggregation accesses solutions strictly impossible for a single model to produce. Well, Table 2 takes those visual gaps from the previous figure and quantifies them with 95% confidence intervals. It lists the exact feature values for support expansion, feasibility expansion, and binding set contraction across the first 3 panels. Crucially, panel D on the bottom right reports the L1 distance between the aggregated output and the best possible single prompt approximation. For support expansion, this distance ranges from about 0.58 to 0.94, confirming that the aggregated solution is statistically distinct from anything a single model could produce. So, in panel C, we see the precise values for binding set contraction. In the first column, the aggregated output XA hits 1.0. By comparison, the best possible single prompt only reaches 0.86. This shortfall appears in panel D as well, where the binding set contraction row shows a distance of roughly 0.21 to 0.35, confirming the single model cannot match the aggregation. Ultimately, this work suggests that compound AI systems are not just about error reduction. Instead, aggregation provides a mathematically principled way to access solutions that simply cannot be reached by a single model, regardless of how well you prompt it. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.